Good morning. Uh, can everybody hear me? Yep. So my name is Dion Brewis. I'm a principal architect on the compiler front-end team, and I'm one of the designers and implementers of the language extensions that you've seen up to date through the talks of Ales, Herb, Vikas, Ale, etc.
I'm Andy Rich. I'm a tester on the C++ front-end team. I'm one of the testers that works with Dion, and I'll be helping him out today with some code.
So we're here today to give you a little bit of a under-the-covers view of what it is that C++ does when we talk to WinRT components. So the first thing I'm going to talk about today is what the WinRT application binary interface looks like, what it is that we send over the wire from language to language, how the C++ language extensions actually deal with the WinRT ABI, and then if you don't want to use the language extensions, if you feel that that is an overhead in your scenario, how you can call the WinRT ABI directly. So I want you to leave here today feeling comfortable that the language extensions doesn't create undue performance implications to your application, but in the scenarios where you need, you can still drop down to the lowest level C++ or C code if you want, to give you the real power and performance that you expect out of C++. So we're going to start off with a little bit of a demo here. Some of you may have seen some fundamentals of this demo. So what Andy's going to do is...
Oh, this is messed up again here. It hasn't changed yet. Give me 1 second. Oh, why that happened?
Yes, this is pre-release software, except that it's not our software.
There we go.
Okay. So what Andy's going to do is he's going to create a calculator library in C++ and then consume it in C# and JavaScript. So C++ is obviously very efficient at calculation, so we want to implement this specific library in C++. So the first thing that you'll notice is the template generates a template library that demonstrates some features of the language. We're just going to go ahead and delete all of that. So, and then create our own ref class. So in this case, it is the calculator ref class, and it's inside a namespace called calcdll. Everything in WinRT has to be part of a namespace, and it's actually important because the resolution of DLLs is based on the namespace that the component is in. That's how JavaScript can find a component, is based on the namespace, followed by the name that gives you the DLL name. So we're going to start here with the ref class calculator, and we're going to seal it. We don't need people to derive from this. Also, we want it to be callable from JavaScript. And JavaScript doesn't actually support inheritance, only the .NET language and C++. The .NET languages and C++ currently support that. So the function we're going to add to that is an add function that takes two integers, add the results together, and then return the result. Very good. I'm sure you can do anything like that in C#. Okay. So just look at the beauty of what Andy just did here. If you're familiar with COM, you'd know that in order to create a COM component, you have to create an interface. You have to specify you're deriving from IAnnown and potentially other interfaces you're deriving from. You have to go and put this in a middle file, compile this to a header file, then go to a C++ component, implement this interface, then go create a class factory for it, and then from the class factory create an instance for it, and then you have to somehow register this component. All of this is done for you by saying ref in front of class. This is just something that now is baked into the language. We create COM components for you, and in this case, we're actually creating WinRT components, which is COM components that are accessible by dynamic languages. And I'm going to go into the details of how that works. Okay, so let's consume this from a C# application. And by the way, if you have questions, you can feel free to let me know at any time. You don't have to wait until the end for that. Yeah.
Just on these ref classes, can you actually use them to do just a standard old-style COM component and register these DLLs when you're done?
They are standard old-style COM components. The only problem is that the interface that they're deriving from is not INown directly. It is INspectable in order to support dynamic languages. However, once you publish them, you can consume them as if it was a COM component from any COM-based language. So you can consume it from standard C++. I wouldn't recommend a Red Server 32, but the registration in WinRT works different. But you can create your own .reg file and put them in the registry and activate it as if it was a COM component. At the binary layer, that's really all that there is. It doesn't include the iDispatch interface. Dynamic dispatch in WinRT works different. It works by inspecting metadata and then from the metadata at runtime figuring out what the vtable position is to call into. I'm going to actually go into a little bit detail on that.
Why is this all the
Well, it's not really tied to Metro. You can actually do some of this inside desktop applications. The activation model, however, is tied to the WinRT application model, and the application model is tied into Metro. So you're going to have to jump through hoops to get this into a desktop application, but the binary interface is not really tied to Metro. And specifically, there are some WinRT APIs that you can call from a desktop application, such as the sensor APIs. Most of it, however, has to do with XAML, and XAML only runs in Metro. We definitely have received tons of feedback from Build in order to be able to support that scenario. So we're going to take that feedback and think about that. Okay.
Or we could repeat them.
Did you hear the question? Yeah. The specific question? I'll repeat the other questions. Fair enough. I'll repeat the other questions. So the question is if there is a mechanism for a singleton. There is actually a mechanism to be able to call a static function directly, or to create a static function and call a static function, which is probably more powerful than a singleton pattern. But through a static, you can create a singleton yourself. There are not class constructors, there are traditional constructors, so you can have constructor arguments. There's no concept of a static constructor. Yeah. Okay, so let's go into the demo.
All right, so I've made the C# application here that's going to consume the DLL.
Okay.
I need to add a reference to our C++ library here.
Okay, so just one thing to note here is some guys have run into this already. If you add a reference from C# to C++, make sure you don't compile the C++ project first. That reference is not going to work. So if you did compile the C++ project, just go and clean it out. That's just a known bug at the moment. If you go build clean, and then you can add that reference. Okay, so the first thing that Andy is going to do here is to create a text box onto the C# XAML surface and give it a name. And that's going to display the result that we get back from C++.
TXT result.
Okay, that sounds good. Okay. Now, we can now go ahead and compile the application. So this is going to compile the C++ library as well as the C# component to consume that library. And now we can go into the CS file and add a using statement to our C++ component. So next thing to do is create an instance of this calculator object that we created in C++, which that's your C# syntax to do that. And then we can assign the result of the calculator operation to the text box on our XAML surface. And we'll just add the two universal developer constants to get to 42. Okay. Of course, need to stringize that, and then we can go ahead and run it. Okay, so pretty simple. Created a C++ component. It's usable in C++. It's usable in C# directly. And let me show you how usable it is in a JavaScript itself.
The interop between the C++ and C#, is that like essentially just caught an interop under the hood, or is it a...
Yeah, so when you're talking about it from the... Can you go ahead and add that project while
Yeah,
I answer
sorry.
the question? So the question is the interop layer between .NET and C++, is that essentially just COM interop? So yes, if you're calling from a .NET language such as C# or VB into WinRT, you are calling through a RCW inside .NET in order to reach the WinRT component. It's not a p-invoke mechanism, it's a true RCW mechanism. And they've revamped it a lot for WinRT to be able to understand the dynamic nature of the objects and have a lot of new WinRT-based features such as inheritance and things which you can't really do in traditional RCWs. Okay, so what Andy did here is to create a new JavaScript component. I keep saying JS. I know I'm not supposed to do that. And now he's going to create a div that will hold the result of C++. So again, he has to add a reference to our C++ DLL.
Okay.
And now we can go into the JS file and directly new up an instance of our C++ component here. Let's say var.
Oh, I need to put it somewhere, don't I?
Yep. So we're creating a new instance of the object, and then go and find our content div that he added to the HTML file, and assign the inner HTML or the inner text to the result of the calculator. Now, one thing that is worth noticing or worth noting here is, even though we called this capital ADD, inside C++, to JavaScript users, that's an unnatural naming convention. You are used to using Pascal case. So what the language projection does in JavaScript is to actually change this from C-style casing into Pascal casing. Okay, so let's go ahead and run this.
No, you can't see. It's unfortunately it's on the screen here. You can't see it.
It's
And push it
kind
over a
of
little bit.
off screen there, but you guys get the idea. We've just called into a C++ component directly from JavaScript. So now the question is, how did we do this? What is a mechanism that allows us to call between JavaScript and C++, or between .NET and C++, and even JavaScript to .NET, C++ to .NET, the full matrix of language interrupts is there. So one of the things that you'll notice, can you just build that project again, clean rebuild of the C++ project?
Oh, sure.
So one of the things that you'll notice is one of the files that we create from the C++ compiler is what's called this calcdll.winmd file. It's out there on the right. And that WinMD file is essentially a CLI metadata file, so you can actually open this in ILDASM. So let's go ahead and do that. So what you'll notice is this is created by the C++ compiler. It has this WinMD file, and this WinMD file can really be seen like a cross-language header file. Because C# can't understand the C++ header, neither can JavaScript. So we need to have a file format that all of the languages, including C++, can understand that means something to all of the other languages. Now, what you'll notice is even though we only authored a calculator class, what the compiler did is to also author an interface, which is the COM interface that we use to talk to this calculator class. So we've decorated the hell out of it, like we do in C++. And called this under iCalculator public non-virtuals. It's called public because it's part of our public surface, it's not protected surface. And it's non-virtuals because the add function isn't actually, you don't have the virtual word in front of it, so we don't want to have inheritance from that add function. So as you can notice, we have a GUID attribute. So if you double click on that GUID attribute, this is like having a GUID attribute specified inside idle. and there's a big constructor for the GUID attribute, and essentially that's the GUID of the interface. So if you call this through traditional COM, you can go and use that GUID and call query interface, and you'll be able to get to that specific interface. So all of our GUID generation is name-based, so we will always generate the same names, but you're also welcome to author your own interface classes and specify your own GUIDs on them if you need to maintain a specific versionability or compatibility with other systems, or you just want to have a stronger contract than what we're going to give you with a ref class itself. The second thing there is the calculator ref class itself. And you can notice that it implements this iCalculator public non-virtuals interface, and it implements the add method. Now double click on the add method. Of course, there's not going to be any code in here because we treat this as a header file. This is not IL that we're going to dump into it. We have nothing to do with .NET. We're just using this file format as a new header file format. So that's why you won't actually see any code in there. It just says we're overriding that interface. Okay. Yeah, well, we can't even dump C++ code into an IL file. It's really just has nothing to do with that. It's just we have a binary on disk. We can load the binary and call into the code on that binary. Okay. So let me talk a little bit more about the language extensions and what it is that we do. So the first thing that we do with the language extensions is we read and write from metadata. So we obviously write out these WinMD files, and we have the ability to read in these WinMD files. It's the first thing to any .NET land or any WinRT language that you actually need to do. The next thing that we do is to map between C++ patterns, such as constructors, destructors, properties, events, methods, static methods, initializers, etc., into WinRT interfaces. So WinRT is more of a cross-language system. So there's things that are specific to C++ that actually only work in C++, such as destructors. They have different semantics in different languages. But in C++, we have destructors. We like destructors. So we will map certain concepts to destructors. We map output parameters to return values. Now, the WinRT ABI itself is not exception-based. It uses H results like any COM API. So the return value of a WinRT API is reserved for an H result. So that means if you want to have our return value, we have our add function. It takes 2 parameters and returns the result of that. We need to actually, at the ABI level, store it as our last parameter and pass it by address. But inside the language extensions, we map this for you so that you can actually put return values in natural return value positions. We provide automatic reference counting. Every object inside WinRT is a ref-counted object, so we have the ability to provide automatic ref counting through the hat syntax, and I'm going to go into that in a little detail later. We provide casting so that you can have a hat to base and assign that to a hat to derived, or you can use a static cast, dynamic cast, safe cast to cast between various objects inside your hierarchy. And then the last thing we do is to map exceptions to H results, so that if you throw an exception, we catch it, we return it to an H result. If somebody gives you a bad H result, we catch that and throw it as an exception. Sorry. So just a little bit about how this exception and return value mapping works, and exactly the wrappers that we create for you inside C++. So the first thing to note is the add function on the right-hand side. So this is what we call production on the production side. This is similar to what Andy wrote initially inside his demo. He has an add function, takes 2 parameters, and I just extended this a little bit, saying that if the parameters are out of range, we throw an exception. Otherwise, we return the result of the 2 parameters. On the left-hand side, you expect it to be callable by just saying int I equal add. You add 2 numbers. And if that guy throws an exception, you want to be able to catch that as an exception. So how do we make this happen? Because Of course, across the WinRT ABI, we can't throw exceptions. It's as bad as throwing exceptions across COM boundaries. And this can actually be happening over multiple processes, multiple machines, even potentially in a DCOM scenario. So what the compiler does for you is it creates what we call a native to COM wrapper and a COM to native wrapper. Now, these are very, very small inline functions, and they should resemble code that you would have written in a COM world anyway. So the first thing to note is on the client side, if we call into the add function, what you actually do is you call into this inline add function. You can actually see the source code that the compiler generates for this, and I'll show you how to do that towards the end. So we generate this add function that basically calls into the WinRT ABI using the WinRT ABI signature, which is at the top of the page. So if you look at the top, it says hresult std call add. It takes to this pointer as the first parameter, takes your parameters, and then if you have a return value, it uses that as the last parameter. Now that's going to be the ABI no matter what language you use to call into WinRT. If you call it from .NET, if you call it from JavaScript, if you call it from C++, every language is responsible for making sure that the function signature is exactly that and only that. And that's the only thing that's supported across WinRT. And in C++, this is how we get there. So we call into that function signature, passing to this parameter, your parameters, and we take a return value that we put on a stack, see if that function returns a failed hresult, and anything in WinRT except for 0 is a failed hresult. So there's no more S false. Everything is a failed hresult except for 0. If there is a failure, we throw it as an exception. Otherwise, we return the result to you. Now, obviously, once we inline this code basically goes into the function that you wrote. So really, the only overhead that you have in WinRT is a little bit about the parameter position mangling. So we are playing around with calling conventions to make sure that in a lot of cases, we can actually just jump to those functions. So far, there are some challenges with the return value, but it's still inline code, and it's code that you would have likely written yourself, inside a COM environment. If you've seen large bodies of COM code, it's generally if succeeded, call a function, if succeeded, call a function, if succeeded, call a function. And if you're in an exception-based environment, it's if succeeded, else throw, if succeeded, else throw. So we basically just automate and write that code for you, but we don't feel that that should really introduce a performance penalty because that's code you would have written anyway. On the right-hand side is what's called the COM to native wrapper. So we go and implement the ABI using the ABI signature, hresult std call add, this pointer, your two parameters, and a return value. We then go and call your user code from there, which now returns a return result. So we map it from the return value that you returned into the output parameter. And if you throw an exception, we'll catch that. Otherwise, we'll catch that and change it to an hresult. Otherwise, we'll just return SOK as the hresult. Okay. So again, if you're used to a COM-based environment, you know that you can't throw exceptions across COM boundaries. So you generally write try catch blocks around your code if you're in an exception environment anyway, and do something similar to this. Okay, now, I've shown you that really the only thing that we do inside the ABI is to check that, or check the hresult and then map that to an exception. But let's say you're inside this insanely high-performance loop. If you look at some of the DirectX documentation, there's some documentation that will tell you, on this API, we guarantee that this API can't fail. Do not check the hresult. If you check the hresult, you're going to slow down your application. And that's really true scenarios. There's some cases where you really, really need to get that close to the metal that says, OK, I'm going to just rely on the fact that this API can't fail. I'm not going to actually check my hresult. So you can do this through the C++ language extensions. So what we're going to do now is to create a new C++ client component into our solution. So go ahead, right?
This is what I've done so far here. I'm going to go and add the reference now to our DLL.
Okay, and then similar inside the C++ client is going to use the XAML designer and create a text box there. How great is it that we have a XAML designer in C++? Again, did you set the name of the text box in the designer?
Yes, I think I did. Oh, let me see.
Okay.
Yes, it's named txt result again. Okay.
And again, we can go using namespace our calc DLL, which is our server-side C++ DLL that we implemented earlier. Create a new instance of the calculator component. Calculator with more C's. And then,
oops. I
again,
need to save the XAML file in order to have the code behind updated. There it is.
right. And then again, use the result of the calculator, add the two numbers together, stringize the result, and assign it to the txt result. Now you'll notice we used ref_new to create a new instance of our C++ calc DLL. And think of ref_new in this scenario as co-create instance. As the old co-create instance in the COM world, this is what ref_new does. So it's a little bit more intelligent than that. It knows, well, contextually, I know that this component is actually inside my own DLL, so I don't have to go and do co-create instance. I can just new it up on a heap and create an instance. Or sometimes it will actually new up things on the stack when it knows, okay, this is actually only used in the stack environment. Specifically strings, when passed as arguments, will be newed up on the stack instead of the heap. But essentially, it's a smart allocator. It uses various allocation techniques to give you an instance of an object.
Is there like any equivalent of the global assembly cache or some sort of global place where DLL is stored, or do they always just take them in the AppX package?
WinRT components that shipped inside the Windows 8 SDK are stored in the registry. There is a new location in the registry for those components. For every other component, it is stored inside the AppX manifest. So you actually have to have it inside the AppX manifest. In terms of the global, there's also a way to get to objects at runtime, so that they register themselves at runtime. If you need to have more detail about that, meet me afterwards at Expo. I'll point you to the person who can give you the detail about that. Okay, so inside the C++ DLL.
Sorry, I just launched it here.
Server. Okay, so Andy went, added the two numbers together again. We called the DLL now. And in this case now, there's absolutely no managed code involved. There's no garbage collector, not even a JavaScript garbage collector. This is all ref-counted objects. This is all native code. It's just pure C++ calling into C++. Now, I promised you to say that I'm going to show you how to skip this wrapper, how to skip this hresult to exception wrapper. Now, this is actually fairly simple. The first thing that we need to do is to create a stack variable to hold our result now, because if you go to the low level, the results are actually stored as a parameter, so you need to have something that you can pass as the address of to that parameter. So the next thing to do is to call into our calc object, and unfortunately we don't have IntelliSense for this yet, but every function has the low-level equivalent inside the same class. And we prefix it currently with under CLI. As a lot of people noticed, we have a large heritage based on C++ CLI, so that you'll find that name CLI throughout our code base. We are considering different names, but at the moment we are just calling a lot of things under CLI. And you can then go and add the two numbers together using the low-level API, and in this case we're going to actually skip that hresult check. Again, I'm going to say txt result text equals result.toString. Now notice that one of the fringe benefits that we picked up from C++ CLI, this is an integer. You can call .toString on it. If you want, you can say 5.toString. have to put it in parameters, otherwise, in parentheses, otherwise we're going to think it's a floating point number. But you can actually stringize every native data type inside C++ now. So this obviously is not ISO compliant C++ yet. Anything that you use inside the Win8 Express Edition compiles with a specific flag. Can you open the properties dialog?
I'm sure, over here.
Of the project. Oh, I guess that's fine.
Let's do it here.
Go to the general
Sorry, it's
options.
this one here. Oh, you just want to see the, yes.
So there's something called Enable Windows Runtime Extensions. So that Enable Windows Runtime Extensions enables the extensions throughout the entire type system, which includes the ability to do things like boxing. Boxing is fundamentally part of the WinRT type system. And so we have the ability to, we need the ability for types that are fundamental types to derive from an object that we can box it, so that we can say platform object O equal 5. It's very important in the XAML model to be able to actually do things like that, because there's a lot of things inside XAML that you just deal with as an object. So inside our type system, we've modified the type system that every object inside the system, every fundamental type, and every WinRT type actually derive from platform object. Okay. So boxing isn't actually implicitly available in this release, but there is API calls you can make to actually box your data types up. So, okay, let's go ahead and run this without doing that H result check. And if you keep your stopwatches ready, you can see that this application should open up in about half a nanosecond faster than the previous version.
It means a lot more when you're doing 60 million polygons, though.
Yes. Okay. So the last thing is to show you that there's truly no magic. Let's create a C function and call it from a C function. Okay, so we're going to create a function pointer here. Type def.
Let me comment out this other line of code here.
Oh, the first thing we actually need to do is we need to include a reference to Windows.8. So far, what I've shown you is everything that we've done to date is the C++ compiler and WinRT. There are no include files to either the CRT, to the standard library, or to Windows.8. This is all internal into the compiler. But because we want to say H result, we actually need to have a reference to Windows.8. So Andy just added that, and is now going to create a C function that actually represents this ABI call that we're making. So it's creating an add func T type, taking the this pointer, the two output parameters, and the two input parameters and the output parameter. And now it's going to take this calculator hat object, which is actually a pointer to a vtable, and I'm going to go over the details of that, and reinterpret cast this so that it says, okay, I actually have now a pointer of virtual functions, which is a vtable, and I'm going to specifically pick the 6th function of that, and I'm going to go over why it's a 6th function and call into it. But as you'll notice there, with that reinterpret cast means the same thing that it always means. It means take this calculator hat and pretend it's not a calculator hat, pretend it's a pointer to a pointer. And that's actually all that the compiler does internally. When it calls things, it's just really pointers to pointers, indirects and vtables, things like that. There's no objects that we allocate, there's no RCWs, etc. It's really just standard C++ that we've extended a little bit to give you a lifecycle semantics, but really there's no magic to this.
So this is because the IntelliSense compiler doesn't believe that we can actually do this reinterpret cast.
Oh, he of little faith. Okay, so let's go ahead and run this. So this code and the previous code is actually the same performance characteristics. Internally in the compiler, this is what we've done. I've just actually given this to you as an illustration to show binary-wise, what happens at the binary layer is purely pointer manipulation. It's very simple. It's something you can do yourself. And you can actually compile and ship like this. Previously, we've discouraged people from taking dependencies on vtable layouts, taking dependencies on vpointer layouts, etc., because it can change from release to release. While in WinRT, that is the ABI format. Once we publish it, I'm not saying we're not going to change it before RTM. It's possible that we can change it before RTM. I think it's unlikely. But after RTM, this is how every component in the system communicates with every other component in the system. You're just basically passing a pointer around, and it has special meaning to every other language. So you can use the same type of techniques and saying, OK, well, maybe I want to cast that level of indirection. Maybe the double indirection is too slow for me. So I want to cast that level of indirection and just store that function pointer directly. You can totally do that. C++ basically is there for giving you the power that you need. And the binary contract of WinRT ABI is a stable contract. You can rely on that. OK. So let's talk a little bit about hats. So we like to call it a hat. We don't really like calling it a caret or a caret or uppercase 6. We just want to say this is a hat. And a hat really is a pointer to an array of function pointers. Also known, if you know C++ well enough, it's a pointer to a vpointer to a vtable. And that's really all it is. When you talk about a hat, that's how we interpret it. So let's say we take Andy's calculator example, and we make it a little bit more interesting. We give it two interfaces. So like iStorage cell as my first interface, iCalculator as my second interface, and we can then give it some storage and the ref count member we automatically give for you by saying ref class. So when you have a hat to this iCalculator, and you say, I have an iCalculator hat as opposed to a calculator hat, we point it to a vpointer. So we don't always point things to the beginning of classes. If you've ever opened up .NET, you'll notice that .NET always points to the beginning of a class. We actually point to the specific vpointer inside a class with a hat. So when we dereference a hat, we then get to, or we dereference a vpointer that we point to, we then get to the vtable. Now, every WinRT object is laid out in the following way. The first three methods on that vtable is IUnknown. This is the familiar COM IUnknown that you know. Query interface, addref, release in vtable position 0, 1, and 2. And the next three interfaces are there for dynamic languages. It's get IDs, get runtime class name, get trust level. So the most important one of that is actually get runtime class name. This is what allows JavaScript to call into .NET and get dynamic dispatch. Now, JavaScript obviously doesn't have a language-based type system. It has a runtime-based type system. So whether in C++ you return an object of type calculator hat or you return an object of type object hat, you can call the same methods to it in JavaScript. Now, how JavaScript knows what the object is that you call against is it goes and calls its get runtime class name. So when you call it on this calculator component of Andy, you call into vtable slot number 5, get runtime class name, it'll say calc_dll.calculator. JavaScript then goes and says, OK, which WinMD file inside the system has the namespace calc_dll? And Windows 8 has an API for that. So Windows 8 will tell it it's inside calc_dll.dll. So it loads up, calc_dll.winmd. It loads up that WinMD file and says, OK, where's my add function? It looks through the WinMD file, says, OK, I found the add function on this iCalculator interface, and it's in vtable slot number 6, which is how I can call into it. Now remember, that's what we did previously in the demo. We called into vtable slot number 6, and that's why, because the first 5 slots is reserved for what's called the iInspectable interface, and our user-defined virtual function then goes into slot number 6. So C++ doesn't really do dynamic dispatch, so we never really call into get IDs, get runtime class name, or get trust level from the language itself. From the XAML implementation, on the Windows 8 side, the XAML implementation will actually call into get IDs and get runtime class name to do dynamic binding to objects to be able to figure out, oh, this object actually has these set of interfaces, and because you have IURI, oh, I know how to give you a stringized representation of this.
What was the question?
The question is, if you data bind to a .NET object, you call via a com-callable wrapper. Is that the question? So, yes, in a .NET object, in a .NET class that's exposed to WinRT, the equivalent of what we've done for a component library inside C++, yes, you call through a com-callable wrapper, and the com-callable wrapper implements these 6 methods followed by the methods inside the .NET interface. Not yet. When I started coding up the compiler, I'll start blogging about it. So we have to have a lot of documentation on exactly this inside MSDN soon. So the question is if there's a performance overhead for data binding in native compared to .NET. It's actually, data binding is a fairly complicated topic. Could you meet me at the end and then we can discuss it? The shorthand is the data binding interface in WinRT is called iCustom Property Provider.
Yeah, there's a couple of them that you can use.
There's a few interfaces that you can implement. .NET implements this for you on every CCW. At the moment, C++ does not implement this on every object.
On any object, actually.
Yeah, on any object.
If you open up the grid or the split templates in the larger, the rich templates as they call them, for the Metro style apps, you'll see an implementation of iCustom Property Provider and iCustom Property. It is also possible to use, they marshal IMAP of string to object as another way to data bind as well. I've got a small sample I can show you in the booth of how that works.
Okay. Yes?
All the WinRT object usage that I've seen so far has all been in proc DLLs. You mentioned when describing exception handling going across proc, across machine.
So the question is, all WinRT usage that you've seen so far is in proc DLLs. That's actually not true. Based on a lot of security, there are WinRT components that run from a different process to give you a crash isolation boundary that if the object does something bad, you actually get that the crash protection. So in this release, there's no template for you to create that inside C++, but the Windows 8 components themselves are actually implemented this way. So we are definitely open to taking feedback and saying, okay, this is a scenario you want to support, and we should enable this inside the templates. You can do it yourself inside the compiler, but we don't have templates for that. Okay. So the other thing that Hatch does for you is it provides automatic reference counting. It's similar to comp pointer of T, except that because the compiler knows about it intrinsically in the compiler, we can optimize it better. So one of the things we already do is you'd never dream of using comp pointer of T in a parameter position. If you do that, you're going to get an attref and release around that comp pointer of T. However, the com rules say if you call into a parameter, if you call into a function, you do not attref and release around a function call. So hats are implemented this way. So we do not attref and release around function calls. But you can't get this kind of a functionality inside a library type. And I got some good feedback yesterday saying maybe we should actually extend the C++ language at the standards body level to allow you to have this kind of borrow semantics that says, oh, I have a type that is lifecycle bound by a higher stack frame, and I just want to borrow the content, but I don't need to actually do a copy construction of the type. At the moment, that's not a concept in C++, but because it's had, we treat it special inside the compiler, so we can do these kind of optimizations that you generally can't do with a library type. The other thing is comp pointer of t doesn't allow you to do casting between, you have a comp pointer of derived to, you have a comp pointer of base, and you just want to be able to assign from the one to the other one. So we added casting implicitly into the hat syntax, so you can have an implicit cast like that, or you can have a static cast, a dynamic cast, or a safe cast as appropriate on the hats themselves.
Can the hat thing, can it resolve circular references? Like say your object has a member that has a collection that actually has the object itself in it. Would that class then never get destructed? Or?
Okay, so the way that WinRT specifies circular references, so the question is about circular references. You have a set of objects that have references between each other. Can we go and resolve those kind of references? That's the one beauty of garbage collection, is if you have a tree of objects that's all cross-references between them, you let go of this tree of objects, the garbage collector will go and figure this out and then clean up the whole tree for that. In WinRT, we have the concept of what's called weak references. So there is a way to hold onto an object using a weak reference. There's a specific interface for that. It's called iWeak Reference Provider. So you can cast a WinRT object to iWeak Reference Provider, call get weak reference, and then hold onto a weak reference of that object. That weak reference then means that the object itself can go away, and then when you resolve it and the object went away, you can't resolve it anymore. But it's specifically there to handle graphs of objects or maps of objects. Okay, so talking a little bit more about how casting works in all of this brave new ref class world. So let's say we have this component as specified on the slide. We have a ref class teacher that derived from iPerson and iEmployee, and we have the source code. So C++ knows this is a C++ class, so it knows what layout is on the right-hand side. It knows, it creates a layout that says iPerson v-pointer is offset 0, iEmployee v-pointer is offset 4, string and age is at offset 8 and 12 respectively. So now when we cast around, we say iPerson hat p equal t. Now, this is similar to what we would have done if this was an iPerson star, if this was a C++ component. We know the layout, we know the offset, so we can say p just equal t, and just leave it at that. It's the same pointer value. If you say iEmployee equal t, obviously we have to adjust the pointer value of t by 4 to get to the iEmployee interface, because if you call via iEmployee, again, a hat is a pointer to a v table, so if you start dereferencing the iEmployee or the e pointer to v table, that v table that you're pointing to better be the v table for iEmployee and not for iPerson, which is why we need to adjust that pointer in order to make it point to the appropriate v pointer. Similarly, if you call a raise method, you'll get a pointer adjustment. If you call a method directly on the object, and I'm showing this for a specific reason because that's something to think about when you're talking about unknown layout. We also do a pointer adjustment before we call into that specific method. That's just something that C++ has always done for you. And then similarly, static cast does exactly the reverse of what an implicit cast does for you. So if you're going from an iEmployee interface E to a teacher and you static cast this, it will just subtract 4 from the employee because it knows the employee is at offset 4 inside the layout of the object. Now the last thing is dynamic casting. If you have 2 classes inside your class hierarchy, but statically they know nothing about each other. iPerson, iEmployee doesn't know that they're implemented on teacher, or that they could be implemented on some other object, or that they're implemented in a different order on the teacher object. So the way that the dynamic cast works is to go into your vtable, look at vtable slot -1, that's the Visual C++ implementation at least, looks at vtable slot -1, which points to the runtime type tables of that class. That gives us enough information to be able to find, oh, the relationship between iEmployee and iPerson is 4, so do the pointer adjustment that way. But it has to resolve that at runtime. Now, this is what happens when a compiler knows size and layout. And we only know size and layout if we have the source code of the component. Once you talk across multiple components, or you're talking to a different language, we have this scenario. We do not know size and layout. So looking again at that teacher class, let's say this is from a WinMD file, and either this is implemented in C# and we have no idea what the CCW looks like, or it's implemented as a JavaScript callback, or it's just a C++ component, but because you've said that you have a DLL boundary, you want to be able to independently version your DLL. So if I change this DLL and I change the size and layout of this component, I don't want the other DLL to make an assumption about size and layout of this DLL, because now you're breaking versionability, so you don't have independently versionable components. So the moment we don't have source code and we go via a WinMD file, the compiler says, okay, don't know size and layout, how do we resolve pointer adjustments in? And this is where COM comes in. So we go, again, ref up a new teacher, assign it to an iPerson, and in this case, we call query interface. That says, okay, I have an iPerson object. It obviously has a UID, as I've shown you inside the WinMD file. And to get from teacher to person, we do a query interface. Similarly to employee, and similarly static cast works the other way around. And now dynamic cast works the same way. So every call in WinRT that is a cast call that has to do a potential pointer adjustment does a query interface. Now the one thing to be careful of in this pre-release, and we've got a lot of feedback for this, so we're thinking about ways to optimize this. If you're calling into a method that's not on the primary interface of an object, that method call will do a query interface, which is an interlocked operation. So it means that if you call the same method 5 times, or you call 5 different methods, you may have 5 different interlock operations. There's 2 ways around it. The one is you can just capture the interface. Once you've captured the interface, and then call against that, it'll do the query interface once. Or you can use that C-style trick that we've shown you if you really need to worry about performance. So one important thing to note, the performance optimizations are not on in the developer preview release. So when you look at our code, don't do too many performance analysis. Don't optimize your code for performance. You're not going to be able to really get a good view of it, because we're not enabling the performance optimizations on the developer preview release. But you're welcome to send us feedback and saying, oh, I think this is actually not going to perform in my scenario, so can you guys think of different ways that we can optimize it? And we're certainly open to look at feedback. Okay, so the last demo we want to show you is a little bit about the details behind the language extensions.
Sorry, your computer has locked itself.
Okay. Oh, can you change the purple, please?
Yeah, do that as well.
Okay, so I'm going to give you a couple of tricks that you can actually use some undocumented but very well blocked compiler switches. The first one that we're going to look at is what's called D1, report single class layout. D1 means it's a compiler front-end switch. Report single class layout will give you the layout of a particular type inside the type system. And in this case, we're going to do report single class layout of calculator. Right-click compile, and then inside your output window, what you'll notice is we're going to actually give you the class layout of that class as we lay it out in memory. You can do this today inside Dev10 even, on any class inside the system. D1 report single class layout gives you the specific class layout. So in this case, scroll down to the calculator type itself. So you'll notice we have a calculator of size 12. The first v-pointer that we have is our v-pointer to iCalculator, public non-virtuals. We then have a v-pointer to object, because every type in the WinRT actually derives from object. And then we have our ref count, which is just a multi-threaded ref count, which means it's an interlock decrement-based ref count. The v-pointer itself points to that v-table. The first 6 methods is the IUnknown followed by IUnspectable methods. And then we have a long decorated name, which is our add function. We just want to make sure that we don't actually conflict with a name that you can specify inside your DLL. The last one is that if there is compile time inheritance, we want the ability to call into the add function from a base to a derive without going via this low-level function. So we actually have a vtable slot for the high-level function so that if you call C++ to C++, we have the ability to directly dispatch in high level. We carry exceptions across exception boundaries. We don't map them to H result. We don't map into the parameter output position. So 6 and 7 is kind of redundant, but they're there for a good performance reason. So now go and search or copy that CLI add function into your clipboard. The second switch that could be of interest is what's called D1 ZW, capital ZW tokens. Now ZW is our switch that means enable Windows RT runtime extensions. Tokens means dump a token stream. So go and search for that function from the vtable. Okay, so here it has unfortunate double space formatting, but this is essentially the code that the compiler generates for each one of these wrapper functions. Now, the compiler doesn't literally generate text code, it generates token streams. So what I've done is I've just run the token streams through the error infrastructure of the compiler to dump it back as code. So you can't always take these things and paste them and have it compiled, but it's to give you a reasonable idea of actually what happens. So look at the function. It's inline long is H result, std call, calculator, big decorated name for add, takes 2 integers and has my return value. It's implemented, setting my initial HR to 0, initial return value to 0. It's important to come to 0 out your return parameters, even if you throw an error. Capturing the result of the add operation, assigning that to the return value, and then see if you throw an exception. If you throw an exception that's derived from the WinRT exceptions, anything derived from platform exception, we just grab the H result from there, return it. Otherwise, if you return a C++ exception, that means eFail. So every C++ exception gets translated into what's called failure exception. It's a generic failure exception. So the other wrapper just above this is the reverse one. So on the interface itself, we have the add, and it's on the interface and then inherited into the class itself. It's a non-virtual function that gets inherited. Again, inlined. It takes your 2 add parameters, captures the return value on the stack, see if there's a H result that was failed. If it failed, it will throw it as a specific strongly typed exception. Otherwise, it returns the return value. Okay, now the last thing I want to show you, can you create a new calculator on the stack there? So as I mentioned before, hats have automatic ref counting, so we run a little bit of code every time you assign one hat to another one. So add a breakpoint to there.
Yeah, I've got a, sorry, you can't see it. There's a, oh yeah, there it is.
Oh, you can actually see it over here.
Okay.
Press F5.
Sorry, we're building here, I think.
Okay. Now when we assign one hat to another one, we have to go and do an add ref on it to follow the COM rules. So you can actually F11 into this code and find a C++ header file. So this header file uses a whole bunch of language extensions, but it's one of the header files that we ship inside the include directory of the compiler. And particularly what we're doing here is we're calling what's called a pointer constructor. We have a calculator hat, calc, or calc2 equal calc. So we're creating a new WinRT pointer there. It takes a generic platform object, and we have a few decal specs on it to make sure it doesn't recurse back into itself. The one is no ref count, the other one is no release return. It's just to tell the compiler, oh, this is actually a special method. If I do an internal assignment here, don't go and call into the special method. It's just basically keeping the compiler from tripping up on it to itself. And in this case, it just takes your class, your object that you've passed in, casts it to IUnknown, and then calls IUnknown attref. And this is generally inlined into your code. So when you run into release or retail, you don't see this function. You just really see the call into particularly vtable slot number 1 there. So, and you're welcome to look through the rest of the file. We have the same thing for pointer constructors, assignment, destructors, etc. And basically all of the compiler guts is implemented in this file. So if you want to see how something works, you can always step into it. Okay. So as a recap, I hope that I've been able to convince you that C++ can give you, the language extensions give you the ability to write great Metro-style applications, and that we do it with as little overhead as possible at runtime. Because the compiler understands the concepts natively, we can do a much better job of optimizing than we can do with the library, but still maintain what we hope is a natural and readable syntax. So I think we have time for one or two questions, but afterwards I'm going to be available at the Expo booth downstairs for the next couple of hours. So if you have any additional questions, please feel free to stop by. Yeah?
Do you have to deal with apartments in this COM world?
Do we have to deal with apartments in this COM world? Luckily, I have to deal with it. Hopefully, you don't have to deal with it. I can give you the details downstairs. There's a lot of details around that. OK, well, please see me afterwards at the Expo, and thanks for coming.